All right. So there's a bunch of different types of drug analysis mechanisms. There's screening, there's confirmation, and then there's quantitative and qualitative determination. These are increasing levels of scrutiny. So a screening test is something like a quick and dirty test that you can do roadside or at a desk or something that can potentially detect certain types of drugs. Usually it's some kind of a color test. You apply a chemical to something you think is a certain drug and it changes color in a certain way. These types of tests have pretty high failure rates. If the concentration of a drug is less than a certain amount, it may not come up positive. And a lot of other chemicals that are somehow similar to that, the drug of interest, or have some sort of similar chemical markers will also come up positive. So screening tests are better used as a rule out kind of a test rather than a rule in kind of a test. They are often used as a rule in kind of a test. There's been some real controversy about roadside tests and then further suppression of the results of future lab tests in some jurisdictions. But that's not obviously the intent behind how you're supposed to use these. If you have a screening test that comes up positive for a drug, what you should then do is do a separate test to confirm that drug is what it is. So if you apply a chemical to what you think is cocaine and it shows up positive for cocaine, you don't just say, hey, this is definitely cocaine, and, lock the person up forever. You want to then do, with another little sample of that cocaine, a more formal chemical analysis that will more positively identify that chemical as that drug for what you think it is. Certain chemical analyses, like you perform certain chemical reactions with that drug and it should react a certain way. Spectrophotometry, mass spectrometry, where you're looking at the wavelengths that can be reflected back by that certain chemical compound in the drug, are good confirmatory tests. There's quantitative and qualitative determination that should also be, they're sort of like logical processes that are applied to the results. Look at the quality of the result and the quantity. So the qualitative result is like, what is the overall material? Is this cocaine? Is this fentanyl? Is it a mix of both? Is it MDMA? Is it baking soda? Is it laundry detergent? Is this marijuana or is this oregano? The qualities of these drugs. Does it have a sticky resin? Does it not have that? Does it have a powderiness? Does it clump when you try to press it together, or does it fall apart? These are qualitative types of tests that you would also want to do before you're spending a lot of money on confirmatory tests. Quantitative tests are more like, what is the substance made of? These are going to be numerical type of tests that can give you how much of a certain chemical is in a solution and what ratio of different things are in a given amount of whatever you think is a drug in your possession. Examples of color tests, again, these are screening tests, are the Marquis test, the Dilley-Company test, the Duquesnoy-Levine test, the Van Ark test, and the Scott test. They're all just different kinds of color tests for different things. The Marquis test turns purple in the presence of opiates and orange in the presence of amphetamines. The Dilley-Company test turns purple in the presence of barbiturates. The Duquesnoy-Levine test turns purple in the presence of marijuana. Frankly, marijuana you can tell by a lot of other different ways, but if you wanted an extra bit of support, you could do this test. The Van Ark test turns like this indigo kind of a presence or a color in the presence of LSD. LSD can be sold in tabs that look a lot like stamps or stickers if you want to tell if this person has a bunch of stickers on their possession or if they're LSD tabs. You could apply this test. And a Scott test will turn from blue to pink. It starts off blue and then turns pink. And then back to blue after a few minutes in the presence of cocaine. You can use any combination of these on any substance, provided that you have enough of the substance to do multiple tests. For example, if you have a compound that you think has both cocaine and opiates in it, you might want to take a little bit aside and apply the Scott test, and a little bit more aside and do the Marquis test. Now, applying these tests are going to change the nature of the drug that you're applying them to a little bit. So it's important that you're only taking as much as you need of however much you have to do these tests, because you're basically destroying it in the process. You want to have some more left over to do lab tests on after the fact with an untampered with sample. Again, these are all initial tests that you could do roadside, for example. They don't guarantee that what you have in front of you is what the test comes up as. There's a lot of confounding factors, a lot of things that can create false positives with any one of these tests. Some are more unlikely than others, but you know, none of them have no false positives. So you need to be remembering that if you're doing any of these roadside tests. A confirmatory test is one type is a microcrystalline test. You saw this type of test with the blood tests before in the previous serology lecture, where to see if it's blood or not, you could sort of crystallize components of the blood, and if it is blood, it'll do it, and if it's not, it won't do it. So same thing with drug evidence for certain types of powders, like cocaine, for example, certain methamphetamine. You can apply a drop of a reagent specific to that drug that will help it form crystals, and then see if it does. If it forms this sort of crystalline, repeating regular pattern, then it's a pretty reliable confirmatory test, and if it doesn't, it won't. Chromatography is where you're going to extract components of a drug through a solution that's designed to attract that drug, and then characterize it in some way. Gas chromatography is where you're going to take a sample of that compound. Like, again, just to stick with cocaine, let's pretend you think you have cocaine. You take a little sample of that cocaine, you put it in a chamber, and gas is forced through that sample. The component is also mixed with the liquid before it's put through this. If the sample that you have, if that liquid solution with, in this case, let's say cocaine and water, has a greater affinity for the gas that's passed through it, which would be something that's specific to extracting cocaine, then derivatives of the cocaine will be carried away with the gas as it passes over this liquid. If it doesn't, it'll stay in the liquid and the gas will come through clear. That gas is directed at the end into a chamber that has computer technology to analyze the molecular compounds of that gas. So if the computer detects in that gas at the end that there is some of that drug mixed in with the gas, or derivatives of the drug mixed in with the gas, then you can consider that a pretty reliable positive for that drug. And if there's none, then you can pretty safely assume that that is not what you thought that drug was. Thin layer chromatography, this is what we did in lab. Unfortunately, I'm sorry guys, we didn't do this in lab because we don't have an in-person lab with this. But what this basically is you take a certain drug and you apply it to a plate, and what's referred to as a plate. In lab, we can do this with just like a piece of paper or an index card. You apply a little bit of it towards the bottom of it. You place it in a shallow pool of a solution that's designed to extract that drug. And as that solution wicks up the paper or wicks up the plate, it'll drag the drug up with it if the drug is present. You'll typically add a fluorescent dye to this so that you can see these results better with very small quantities of the drug. Both of these types of chromatography technology ultimately use introducing a chemical to a drug that is specific to that drug, and if the drug is reactive with that or can bind to it, it'll get pulled with that solution, that other chemical, and evaluating the chemical after the process should show you that that drug is there or not. Spectrophotometry, we're going to talk more about this with paint evidence. But what this ultimately is you blast certain types of light at a chemical or a substance of interest, and you wait to see what types of light are reflected back. With light, with things of a certain color, that wavelength of light is being reflected and all other wavelengths are being absorbed. So if you have a green leaf, what's happening is blues are being reflected back off of it and yellows are being reflected back off of it. Blue and yellow makes green. And reds and oranges and purples are being absorbed. Depending on what specific shade of green we're talking about, different amounts of these different wavelengths of light will be reflected or absorbed. This can be characterized by blasting light at basically anything and measuring that with a computer, basically seeing what and how concentrated or how strong those wavelengths of light are that get reflected back. So you can do this with drugs, and different types of molecules will have different characteristics. They'll read out differently on a screen. Again, we're going to go into more detail with this with the paint evidence, but each one will come up with a really characteristic looking graph. So if you blast infrared or UV light at morphine, it'll come up with a peak that looks like this. Caffeine, it'll come up like this, where the wavelength of light that's reflected back is more like 275. With heroin, it comes back at more like 280. That's a length of the wavelength of light. You can do this with visible light range. You can do this with UV light. You can do this with infrared. Typically for drug purposes, infrared is most useful. Finally, you can evaluate drugs as a confirmatory test by mass spectrometry. Sorry. This is where you're going to have that final gas chromatograph, and you have the substance passed through that, just like we already talked about. And then each component is passed through a mass spectrometer. That gas is taken and put into basically like a vacuum that can then have electrons beamed at it, at those incoming molecules, and you can read the electron blowback and determine what's in it. Again, we'll talk a little bit more about this with the paint evidence, but that's basically what it is it's an extension of gas chromatography that gets really specific by applying an extra step of beaming electrons at it. The new molecules that end up being created by this process, though, are pretty unstable and degrade. So gas chromatography will degrade your sample, but not necessarily completely. This will destroy your sample. So you're not going to want to do this to anything that this is the last amount of your drug that you have left. You're going to want to make sure that however much you put into this process, you still have some left over for other tests or for evidence, for other evidential type of uses. And the nice thing though with this is that you only need minuscule amounts to do it. So you pretty much always be certain that you'll have enough to do this process with.